This video is all about electrochemical cells and its formulas. Now let's proceed. Now we have the following equations and the following representations of the variables involving those equations. Now, the standard voltage is represented by E naught or E degrees or E naught, which is also equal to the voltage at the reduction cell plus the voltage at the oxidation cell. Okay? For standard voltage, E naught is equal to the voltage at the reduction cell plus the voltage at the oxidation cell. So the unit for the standard voltage is in terms of volts, V. Now let's proceed with the free energy. Free energy is represented as delta G naught is equal to negative N multiplied with F multiplied with E naught. Now let's define the variables involving the free energy. The free energy delta G naught is equal to negative N. This is the number of electrons that canceled out during a redox reaction multiplied with F, the Faraday's constant, which is equal to 9.648 times 10 raised to 4 joule per mole volt multiplied with E naught. E naught is the standard voltage of cell reaction. Now the units or the unit for free energy, since this is in energy and SI, so we're going to use joules. Now let's proceed with the following variables. E naught, delta G, K. E naught or the standard voltage is equal to the negative of free energy delta G naught all over NF. It is also equal to the following quantities as the fraction of R T natural logarithm of K all over N times F. Now let's define the following variables R, T, N, F, and K. RT stands for the gas constant. And since we're going to use SI units, the gas constant for the R is 8.314 joule per mole multiplied with Kelvin. And the temperature must be in Kelvin for unit consistency. And K or the reaction constant is unitless. And N is the number of electrons that canceled out during a redox reaction. And F is again the Faraday constant at 9.648 times 10 raised to 4 joule per mole volt. Okay. This is also equal to the following values at 25 degrees Celsius. Take note, these values are at 25 degrees Celsius, so 0.00257 volts multiplied with the natural logarithm of reaction constant all over the number of electrons that canceled out during a redox reaction equation occurs. So at 25 degrees for the standard voltage E naught, we're going to use this. Now let's proceed with the Nernst equation. The Nernst equation deals with the cell voltage E. The cell voltage E is equal to E naught. E naught is the standard voltage minus the following fraction, the gas constant multiplied with the temperature in Kelvin times the natural logarithm of Q or reaction quotient. This is unitless all over the number of electrons that canceled out during a redox reaction occurs multiplied with the Faraday's constant. Now at 25 degrees, our cell voltage is equal to the following quantities as E naught minus 0.0257 volts times the natural logarithm of Q all over N. Okay, please do not be confused with E and E naught. Again, E stands for cell voltage and E naught stands for standard voltage. For a spontaneous reaction occur, E naught is greater than 0. Our reaction quotient or constant, reaction constant is greater than 1, and delta G naught is lesser than 0. To solve now for pH is equal to the negative logarithm of H plus or hydrogen ion. Now, if we are given with the following reaction, A plus B as a reactant, okay, producing product C plus D, the small coefficient letters here, small coefficient letter A is the balanced coefficient for reactant A. Small coefficient letter B is the balanced coefficient for reactant B. Small coefficient letter C here is the balanced for the product C. And small coefficient letter D here is the product of the balanced product D. To write now the reaction quotient Q is equal to the ratio of the products all over the reactant, the amount of the concentration of the products all over the reactant. Okay. To write now the reaction coefficient or reaction quotient of this given ideal reaction here, Q now is equal to the product all over the reactant. If we're going to write it down, capital letter C raised to the coefficient of smaller or the coefficient of the product C here as small letter C multiplied with the concentration of the product D raised to the coefficient of small letter D all over the product of the reactant A raised to the coefficient small letter A times the concentration of reactant B raised to the small coefficient letter B. All right. Our next video is all about the problem solving part for electrochemical cells.